Yeah, so just to recap what we were talking about. I'll just mention the last aspect here. I was talking about detecting drift in some distribution, and then again the whole background here is we want to know when. Hold on a second. Yeah, we want to know when to. I just realized that. Let me mute my my. Did you guys saw the WebEx the Slack thing, right? On the
We're okay. We just see the.
Okay.
Yeah.
No, yeah. Sorry, I just wanted to mute this. I'll just close Slack, I guess. Okay, so we're trying to make some kind of decision about drift and making a decision based on some kind of distributional distance. I talked about taking two data sets and then multivariate case, saying if they're different, and the univariate case for both numeric and numeric and categorical variables. And again, the whole idea is to use statistical tests to know when something is changed, data is changed significantly in some way, and to make a decision about that. Okay, so the last thing I'll kind of mention here is this is something I learned recently that's been pretty useful. I'm talking here about some kind of using some kind of categorical data and deciding if it's changed. The kind of you decide if there's been drift based on whether the frequencies in the various categories have changed significantly relative to some baseline. And so I mentioned kind of some of the classical tests like chi-square, and then one of the effect size metrics like Cohen's W that can be used like instead of that. So one of the things that's important is that some of these tests are asymmetric in that they're testing the observed frequencies in this case versus the baseline. You can see that in the formula, because here like the statistic has the xi prime is the frequency in one category, xi without the prime is the baseline frequency of that same category. And because basically if you end up dividing by the baseline, it means that you're taking, if you end up dividing by the, because this denominator depends on whatever the baseline is, it's if you change, it's an asymmetric metric, because if you decide to change, test the baseline versus the observed, it doesn't, you don't get the same value. So it's not a true distance metric. It's an asymmetric kind of measurement. So I just wanted to mention, as I mentioned here, a few other distance metrics for categorical, and some of these are symmetric, which is useful. So one particular one I want to mention is Jensen-Shannon distance, which I've used in a few applications recently. It's actually not only for categorical. You can use it for numeric distributions as well. The only thing is that you basically have to do some kind of like a kernel density estimate. It takes a vector of probabilities at various values, which if it's categorical, they're just the probabilities at each of the categories. If it's numeric, you have to do like the kernel density, and then the probabilities are basically again these kernel density values and normalized by something. So this also can be used for numeric, but maybe with like an intermediate step. But I first encounter it. Basically, as far as I can see, most of the Python implementation kind of assumes that it's a numeric, that it's a categorical as opposed to numeric. So the reason why I like this is it has a lot of good properties. So it's symmetric. It has the triangle inequality. And another thing which I'll mention, so basically the input here is two vectors of probabilities.
A quick question.
Yes.
The KL divergence is not symmetric. So how do you,
Yes.
it's made symmetric by adding both of them, right?
Yes, yeah, right. So the underlying, it uses the KL divergence, which is not symmetric, but here's how it becomes a symmetric measure. Again, these are the pi and pi hat are the baseline and observed. And what you can do is you can take the element-wise average between each category, and this has to be the element-wise average will be 0 if both categories are zero, but it will not be zero if at least one of them is not zero. And this is a frequent kind of problem that you see in these metrics. For example, say in the chi-squared metric, say that you observed a category in the chi-squared metric basically assumes that like all the categories, at least in the baseline, have at least some minimum number. If you have a category in the observed that was not observed in the baseline, then this is undefined because this will be 0 for one of them. And that's kind of an unattractive property because that can happen. So this one does not have that. It overcomes that property because the mean has to be if at least one of them is non-zero. This mean will be non-zero, and therefore basically what you do is you take it's the average of the Kullback-Leibler distances between each of the vectors and their mean. So this is the distance between the observed and the mean, and this is between the baseline and the mean. Actually, between the first is the baseline, the second is the observed or production data and their mean, and you take the average of them. And that's that again because even though the Kullback-Leibler distance isn't symmetric, this will end up being symmetric because as you can see, you can just flip the two inputs. And also, and as I said, also it's okay if it still works if there's a category that's 0 in at least one of them, it still works, and that's important. And it's bounded between 0 and like the log of 2 with the base that you use in the Kullback-Leibler distance. So if you use base 2, which is like for information theoretic, it's bounded by 1. So that's yeah, right, because it's log of base 2 of 2, which is 1. Okay, so it has a lot of attractive properties. And one thing I'm still trying to figure out is, which have been very hard to find, is like what's statistical significance of a given value? Like is a Jensen-Shannon distance of 0.10, is that significant or not? And that's surprisingly, I'm actually not sure about that. So I'll get back to you about that. But another point which I found useful is basically you can because the Kullback-Leibler distance has this form, like it's the sum across the categories of and basically you're calculating divergence between each category and something. So and it's the sum of those. Basically, I can break this up, this expression inside the square root as this. The j for a given category is just this expression, and then the Jensen distance is the sum or half of the sum of these under the square root. So one way you can tell which you can kind of basically use this to score which category contributes the most to this distance, is which category appears to be the most causing the drift. Because I use this as like a score function, so it's pretty useful. And again, because it has all the properties that I mentioned before, it's overall it's a useful metric. Any questions about that?
How do you pinpoint which feature is most
would just whichever one has the highest value of this expression, whichever category has this is the biggest. It's the distance is the square root of the sum of these. So sorry, half is half of the sum and the square root of that. So it's basically this is the big whichever one has the biggest, whichever category has the biggest value of this is the biggest contributor to the sum.
So the can you explain the MIs a bit more? I mean,
MI is the average of each. The MI is the average of each the category frequency here. It's just the average of the category frequencies and the baseline and the observed.
only on the things that are have intersection, right?
No, well, it's both of them. All categories, not it's in a unit really, because yeah, because basically if a category, well, if a category isn't observed in either, then there's no divergence. So there's only a divergence if like it's observed in one and not the other, or basically if the values, the probabilities differ in one category between the observed and the baseline.
So if I change the order of the m and the pi's in the definition, what will break?
And nothing that well, the MI are indexed to the pi. That just means, oh, so you can put m here and pi here.
Yes, on both.
I guess it would change it, but that's because it's not. Yeah, I mean it would change it, but that's not the formula. So it's always the divergence. Like the m is again the m is between the pi. The m is between the values of pi, the proportions on either the baseline or the it's like the divergence on either side of the average on each level.
What I think I understand. What's the difference between this and going d pi pi prime d pi prime pi?
I don't understand the question.
What's the difference between the JSD and not having an MI in the middle, but instead having the sum of d pi and pi prime in both orders?
Well, sorry, the inputs to either here have to be a probability vector.
I could, you see in the chat, I could define a I'm putting it in the chat.
Okay.
So I could do this, right? You see in the chat?
Yeah. What's
Pi is your pi here, but I'm just doing p.
Yeah. Okay. Oh, you mean the big P is the M? Why would you do that?
No, not the m, but the pi.
Okay.
So I'm doing d pi pi prime, d pi prime pi. D pi pi prime plus.
Oh, right. Okay. So that's just the symmetric. That just okay. So that makes it. What's the difference between them? I think that would just be. Isn't that a given? Isn't that a certain metric? The average of the like. So
Yes, it's a matrix. I'm just wondering why we're using this one, not the other one. It's going to be a metric. It's going to meet all the axioms.
Right. I'm not sure at the moment.
Okay.
Yeah, so I'll have to. I'm not sure.
Okay.
Okay. So, any other questions? Okay. So now the thing I want to talk about, which is less mathematical, and I'll kind of I guess talk more through it, is in some of the papers that we've written in our group, we've used okay. So far I've been talking about like you just have a data set, and then you want to detect drift, and there's a statistical test that measures what's the drift. So here I'm going to mention some papers that we've written, which show that basically instead of kind of like instead of doing drift detection directly on these data sets D and D prime, you can kind of model some intermediate aspect and then do drift detection on that. And basically, the drift will be like if the aspect that you're measuring changes, an aspect is usually some kind of useful thing that maybe is an input from something else, but not the data distribution itself. You can detect drift that way. So just mention a few things. If you're familiar with our work on Freya, comes from that. The idea here is if you have a data set, what we do is Freya basically it creates what are called slice rules, and a slice rule is a conjunction of subsets of a feature. And if it's a numeric feature, it's like an interval from minimum to maximum. If it's a categorical feature, it's a set of values. And so for example, a slice could be here's an interval on the income feature, here's an interval on the state feature, which is categorical, and here's an interval on the sex feature, which is also categorical. So this means basically the slice is saying these are people. Basically, the slice defines a region of the slice defines a region of the feature space or a subset of features. So a subset of the observations by taking subsets of the feature ranges. So like this means basically a person who has income in between 30,000 and 60,000 and lives in one of these states and is male, that person falls in the slice. So you have to satisfy, you fall in the slice, so you satisfy all the conditions in the slice. And basically, we have a tool called Freya. Again, this is the slice feature. The slice aspect is a general construct which appears in different methods. But in Freya, what we do is we try to find subsets of the observations specifically that look like this, that are characterized by kind of hyper rectangles on the features that contain the observations that fall in these slices contain higher than average mistakes of the classifier. So my point is that what we'll end up using these slices and something about them, whether they grow or shrink in size, to predict drift rather than doing drift directly on the data set. We do it for various reasons. This is like the intermediate aspect which we're modeling. Okay, so that's where these slices come from, and then it's kind of a way to indirectly detect drift. So instead of again, the idea is, for example, we have like a data set D. We have a classifier's prediction on it, and that's how we get the slices originally. So rather than kind of detecting, we wanted to see like, is the data set overall changing? Is the classifiers, maybe is the classifiers accuracy changing between the two data sets? One way to do it is again through these intermediate slices, rather than kind of doing drift on the data itself. So what we do here is we say that there's k slices that are found on the first data set. Notice that they can overlap. An observation can fall into more than one slice, and also some of the observations don't fall in any of the slices. So we take for each slice I, we take the fraction of observations that fall into it. That's the first one, and this is the fraction I2I is the fraction of observations that fall into this slice in the second data set. Then the idea is that basically if there's no drift, then we expect on average that a given slice should have about the same proportion of coverage in the two data sets. And then if this is generally true across all k slices, then there appears to be maybe no drift. And this is kind of like a way of distilling, maybe, there's so one of the reasons we would do this is, for example, the data sets it might be many features, it might be a mixture of categorical and numeric features, like categorical and numeric features, and that might be hard to characterize in a distribution or a statistical test. So if you kind of describe the data distribution in terms of the fraction of observations that fall into in given slices, and use that as your intermediary, then you can test drift. So basically, that's the idea. And one way you could test this is basically have a set of hypotheses that the null hypothesis is that the slice hasn't changed in size, in fractional size. The alternative is that it has changed in size, and then we use so that's one of the hypothesis tests I mentioned before, a test between proportions, and then you can use a method called multiple comparisons. The reason is that we want to make a single decision of whether a drift has happened, not by looking at a single slice, but whether combining the evidence across all the k slices. So it's not enough to say that one slice has changed in size. We need the slice, we need to be significant enough across all the slices, or something like that. So there's methods for adjusting for that, which again, it's not enough to just reject one of the p-values, one of the hypotheses. You have to reject more of them at some. You have to adjust for that fact. So that's one of these methods, and then that's our decision to. That's how we detect drift. So in the paper that we mentioned, we can use this as a way to detect drift in two ways. Either the idea is if slices overall grow in size, in fractional size, that kind of means that maybe there's more errors because there's more observations falling into the region that we identified as being the slices initially had high error concentration. So you can identify, like, if the slices grow, that maybe that there's more errors, or if the slices change, either grow or shrink, then that might be just general distribution that change, not necessarily connected with the classifier being better or worse, but just arbitrary kind of distribution change. And again, the purpose of is that slices, once we have them, can be more easily used to characterize something about the distribution by looking at their sizes, rather than trying to model a distribution itself. Okay. And that's kind of the idea of this aspect. And later I could talk about other aspects. But
Great, thank you. Any additional questions or comments? Okay, so thank you very much for today, Sam, and we'll continue next time.
okay, thanks.
Take care.